Welcome to this lecture series on group theory. Last time we introduced the definition of a group and we said that a group is a pair where the first entry of the pair is a set G, a non-empty set, and the second element is a binary operation on G, such that three axioms hold or three properties hold. The first is that the binary operation be associative, so this we know what it means. The second axiom is the existence of an identity element. So we insist that there is an element E in G such that this equation holds for each element x in G. Right? So what it says is that if you multiply E with x or x with E, you get x. So I'm using the word multiply, which is a very commonly used terminology to refer to the binary operation. In the context of one group, the multiplication is just referring to the binary operation of that group. Okay, that's just one way to say it. I mean, it's a cultural thing, if you will. Okay, and we can easily show, as we did, that there is only one such element E. Even though the axiom only insists upon the existence of such an E, you can easily show that there is at most one such E. So paired with the existence, there is exactly one such E, which is to say that the identity element is unique. Any such element is called an identity element, but there is only one, so now we can call it the identity element of the group. Okay, and then we also had this axiom about inverses. So we insist that for each x in G, there is an inverse to it in the sense that this equation holds. So y is called an inverse of x if this equation holds, and we insist that for each x there is an inverse. Today we will show that inverse is unique, meaning given an element x from the group, there is a unique inverse, meaning there is a unique y which makes this equation true. It's a very simple proof. You can do it right now for yourself. Alright, we saw the definition of an abelian group, which was just that a group is called abelian if the binary operation is commutative, meaning that A star B is equal to B star A for any choices of A and B from the set G or from the group G. Okay, we saw a bunch of examples, and very importantly, uh, we saw or we mentioned that the binary operation is often suppressed when we write things down. So if we have a group G, first of all, we may say things like let G be a group. So this means that there is some binary operation which we do not even write down. But there is one, of course, since G is a group, there is a binary operation that is there on it. Instead of writing A star B, we just write AB. Suppose A and B are chosen in the set G or in the group G, we may just say AB to mean, the binary operation is sitting between A and B, but we don't write it. Just like we do not write the multiplication symbol usually when we are multiplying usual numbers. Okay, so that is some remark. And yeah, as I said, we refer to the binary operation on any group as group multiplication. Sometimes when we are dealing with an abelian group, we do not refer to as multiplication, we refer to as addition. For instance, if we are dealing with the group Z with its ordinary addition, it would be very weird to call it the group multiplication, even though that is accurate given our convention. It would be highly confusing to refer to this guy as a multiplication, so we have to be aware of the context, right? Okay, today we will see some very basic properties of groups. Very important, but also very basic. So let's proceed. Some problems for practice. And now let us get started. So first we will show that the inverse is unique. To any element of a group, there is a unique inverse. So fix a group G. Again, we have suppressed the binary operation from notation. And most of the times we use star to denote the binary operation, but we could use any symbol. We could use some messed up symbol like psi, although that would be very confusing. Anyway, so suppose we have a group G, then we already know that it has a unique identity element, previously done. So the thing that we are going to do is show that for each element x in G, there is a unique x prime such that this equation holds. Alright, try it yourself, it's very simple. So to prove it, suppose we have two elements, x prime and x tilde, in the set G, such that this holds and this holds. And what does the uniqueness say? It just asks us to show that x prime equals x tilde. This is what we want to do. But it's very simple, because from this equation, let me box these equations. Let me refer to this as 1 and the other as 2. So from 1, in fact 1 is exactly reading that xx prime equals, well, let me just use only the first half of 1. So I'm just using that this is true. Now, this is some element of the set G or the group G. So when I say the set G or the group G, I mean the same thing. Again, it's a slight abuse of terminology or phraseology, but it's okay. So this is an element of G. We can operate it or multiply it with anything we want. So what we will do is we will multiply it with x tilde being on the left side. So this gives us, I mean, this we can multiply with x tilde and this we can multiply with x tilde. So we will multiply on both sides. So this implies that x tilde xx prime equals x tilde e. And now here I should have put this bracket. Right, this I'm just treating as a single element of G. I should have put this bracket, but recall the binary operation on a group is associative. So there is no need to put brackets. We can't shuffle things around as we like, but not putting brackets is not causing any ambiguity, because you can bracket whichever way you want. The associativity shows or tells us that it won't matter. So now we are actually thinking of it like this. Even though it was this, but we can think of it like this and use the second equation to say that this is equal to E, and that will do it. So the right side is clearly x tilde because E is the identity element. So the right side is x tilde. So this gives us that E x prime is x tilde, but E x prime is just x prime. So here the bracketing was thought of like this, using this element because of this equation is E, and E times x prime is x prime because E is the identity element. X tilde times E is x tilde because E is the identity element. And we have shown what we wanted to show. So it's a very simple proof, but I went over it in full detail. Okay. Yeah, so now that the inverse is unique to any element of the group, there is a unique inverse. We can have a notation for it. And the notation for it is the following. The inverse of x is denoted by, we write an x, and then we write a -1 as an exponent. So this is a reminiscent of our usual practice, that suppose we have a non-zero real number, say 3, then you can write the multiplicative inverse of 3 as 1 by 3, or also as 3 to the power -1. Right? That's a very common practice. So this notation, I'm sure, was motivated by our usual algebra. Okay, so just remember what this means, what this notation is. And with that, let us proceed. Okay, so now we can have some corollaries. Suppose we have a group G and we have some element x in G, and suppose y is such that this equation holds. Then y is necessarily the inverse of x. We don't even need to insist. The content of this line is that we don't need to insist that xy equals yx equals e. Just one side is enough, so to say. And similarly, the other part of this proposition, both parts are just saying that one side is enough. I'm using the word one side loosely, but I'm sure you understand. So let me prove this thing, and the other thing will be an exercise. So proof of 1. I haven't labeled them, so let me label them. So what is the proof of the first part? Let xy equal identity. Then multiplying both sides by x inverse, we get this. This is exactly the same proof we did in the previous page, but I'm doing it. And this is equal to, or this implies y equals x inverse. So what happened here? The first step should be clear. We just operated or multiplied by x inverse on both sides. And this has been now bracketed like this. The fact that x inverse is the inverse of x by definition, this is the identity element. And therefore the left side is equal to y. The right side for the same reason is x inverse, and we have proven it. Similarly for the second part. So it's a very simple thing. And now, yeah, some more basic properties. I have an urge to change the color of the previous proof. Yeah, I think this is better. So now we are saying that if G is any group, then the inverse of the identity is the identity itself. The inverse of the inverse is the original thing. Very natural. And if xy is E, then yx is E automatically. So the first part should be clear, because if you, it should be clear directly, but if you just look at this, all you need to do is show that E times E is E, which is clearly true. So this you can think about if it's not clear. What about this? Why is it that if you take the inverse of the inverse, you get the inverse? Well, the reason is we have x inverse is E. Well, let me write it like this. We have x inverse x is E. And now think of this as an element of the group, and this as some other element which has this property that if you multiply it with your original element, you get E. And apply this apply the first thing here, you will see that x is the inverse of the inverse of x. I'm just applying this particular statement on this equation. The second one is the inverse of the first one, but the first one itself is the inverse of x. So that justifies this equation, and this you can take as an exercise. So very simple properties. All of this will become so natural that you will even forget that this was ever discussed. But yeah, they are to be discussed. All right, let's proceed. Yeah, so there is some more material here which I don't even know what is there. Let's see. Yeah, so we are saying this is more like a puzzle, a simple puzzle but interesting. So what are we saying? We are saying that suppose G is any group and assume that it has even size. So it is a finite group. Once we say that mod G is even, it is necessarily a finite group. So what is a finite group? A finite group is a group where the set is finite. That's the definition of a finite group. That was self-explanatory. So fix a group G and assume that it has even size. We want to show that there is an element in the group G which is its own inverse and which is not equal to identity. We just saw that identity is its own inverse. That's okay. That's kind of a trivial statement, true for every group. Here we are saying that whenever we have a group of even size, there is some element in the group G which is its own inverse, but that element is non-trivial in the sense that it is not the identity element. Something apart from the identity element has this property. Okay. So since any group has a very abstract definition, this statement may seem very opaque. How is one going to go about it? When faced with any such question where one hits a wall, one should instantiate such a question in a concrete example. Just study this phenomena or phenomenon in concrete examples. Okay, so we will do that. The larger principle here is to create a simpler problem. We are faced with a problem where we seem to be lost. So create a problem which is simpler but retains some difficulty, some essence of the original problem. So how are we going to simplify this problem for us? Well, we will not be working with some abstract group. We know a whole family of groups which have even sizes. Namely, one such family is, there could be many of course, but a family is Z mod nz where n is even. What is the size of Z mod nz under ordinary, under not the ordinary, but under the addition on Z mod nz, right? We discussed an addition and a multiplication on it. Under the multiplication, this is not a group. Under addition, it is. So if n is even, this would be a group with even size because the size of this group is equal to n. So let's just study this phenomena in Z mod nz. Maybe I have drawn a picture here. Yeah. So Z mod 6z is what I've drawn. Let's just study or investigate this in Z mod 6z. So clearly 0 is its own inverse. Okay. Because 0 plus 0 is 0. 0 is the identity of this group. What about the element 1? 1 is not the identity of this group. It may be confusing. 1 is certainly not the identity because 1 plus 1 is not, in fact 1 plus 1 is not 1. So 1 is certainly not the identity. But what is the inverse of 1? It's 5. If you add 5 to 1, you get 6, which is 0 modulo 6. So here everything that you see is a remainder class, even though I have written integers here. But again, it is also a common practice to not write the brackets or the bars or anything. And from the context, it is clear what these symbols mean. These are not your usual integers. These are elements of Z mod 6Z, and the elements of 6 mod Z mod 6Z are remainder classes modulo 6, not numbers. Okay. So the inverse of 1 is 5, and to denote that, let's just join it with an edge. Okay. So this edge denotes that 1 has 5 as its inverse, and then automatically 5 has 1 as its inverse, because we saw that if x is y inverse, if y is x inverse, then x is y inverse. Right? I think this was explicitly stated. Maybe not. But this is statement that the inverse of the inverse is the original thing is the same thing. That if y is equal to x inverse, then x equals y inverse. That's what this statement exactly is. Okay, so 1 and 5 are inverses of each other. Inverses come in pairs. What about 2? 2 and 4 are inverses of each other. So we are left with 3. What about 3? Well, it's going to have some inverse because the whole thing is a group. 0 is not available. 0 is its own inverse, so it cannot be the inverse of anything else. Right? If y is an inverse of x, it is the inverse of only x. It cannot be the inverse of some other element. Because inverses come in pairs. If x is an inverse of y, then y is an inverse of x. So it is forced to be its own inverse. These have kind of bonded, this has bonded with itself. And this cannot be really lonely in that sense. It has to have an inverse. So it has to be its own inverse. And you see, the cardinality is really what is making this tick. If this were an odd-sized group, say Z mod 5Z, the same phenomenon will not occur. You can experiment with Z mod 5Z. This statement is not true for Z mod 5Z. So from here, a general proof is already hinted at. What you do is, and I'm going to write down the general proof not in the language of graphs. Here really what we did was we drew a graph with the elements of G as its vertices, and we joined an edge between two elements if they were inverses of each other. But I'm not assuming that you're familiar with graph theoretic terminology. So I will write the proof in the language of equivalence relations. So fix a group G of even size. Okay. And define a relation tilde on G as x tilde y if y equals x inverse. Now this is not an equivalence relation. We want an equivalence relation, so we need to modify this a little bit. If y equals x inverse, or y equals x. So we are artificially making it reflexive. Basically, that is the point. And the exercise is that show that tilde is an equivalence relation. That's a very simple exercise, but I recommend you do it because doing these exercises helps you digest the definition and gives you muscle memory about the abstract structure of the group or any general abstract mathematical object. Okay, so this is an equivalence relation, and now if the proposition were false, so suppose on the contrary, assume on the contrary that there is no element such that it is different from identity and it is its own inverse, then we want to produce a contradiction, right? We want to show that in this group there is some non-identity element which is equal to its own inverse. So we assume on the contrary to that. So then the claim is if x is not the identity, then the equivalence class of x, which we will denote like this, has size 2. All of this is very simple. It's just that written in this language, it becomes complicated. The real idea is already here. You are just pairing up the inverses with each other. The identity pairs with itself. Now, by the cardinality being even, you are forced to have some element which will also pair with itself. That is the thing. We are just expressing that thing in the language of equivalence relations. The correct language to write this proof would be the language of graphs. Anyway, I've already said that. So we claim that if x is not identity, then the equivalence class of x must have size 2. Proof is very simple. If not, then because if this has size 1, then x is its own inverse. Right? Because if x were not its own inverse, then there would be some element different from x which would be its inverse. And hence, this element y would also be in the equivalence class of x by definition of the equivalence relation. And that would force that the size of x is at least 2. So if something has size 1, then it has to be its own inverse, and hence that has to be identity. Because we have assumed that the only thing which is its own inverse is the identity element. Also, can there be something with size more than 2? Or I should say, even before we made this claim, we should have made a simpler claim or a more basic claim that the size of the equivalence class of any x is at most 2. So why is that? Well, if something had size more than 2, then there would be 3 elements, at least 3 elements. So suppose there is some x whose equivalence class has size more than 2. So its equivalence class, let's say, has at least 3 elements x, y, and z. Now, x is related to y. What does that mean? It means since y is different from x, the only possibility is that y and x are inverses of each other. Similarly, x and z are inverses of each other. But we know that the inverse is unique, so that means y equals z. So there cannot be 3 different things there. So I will not write down the details here. I'm sure you can write them down yourself. So now by using these 2 claims, we see that every equivalence class either has size 1 or 2. And the only equivalence class with size 1 is the equivalence class of identity. Now, using the fact that the equivalence classes partition the group, we see the size of the group is the size of the equivalence class of identity plus some even number. Because why is that? Well, every element different from identity has its equivalence class of size 2. By these 2 claims, if x is not identity, then the equivalence class of x has size 2. So the equivalence class of identity we have separated out, every other equivalence class is size 2. So the sum of the sizes of the equivalence classes other than identity would be an even number. And the equivalence class of identity has size 1. So we get the size of G is 1 plus, this was supposed to be an equality. So the size of G is equal to 1 plus an even number. And that's an odd number. And that's not, that's a contradiction to the hypothesis that mod G is even. So I have made a very simple thing look very complicated, but I hope this example was illuminating. Alright, so let's proceed. Yeah, so this is very important. This is a definition. Suppose we have a group G, then for each element of the group and for each integer n, we define this notation as, this is defined as x star x, or let me just write x dot x n times. So the dot here is referring to the binary operation on the group. Instead of star, I'm just writing a dot, which is very common. N times if n is positive. It is defined as identity if n is 0. And it is defined as x inverse to the power mod n if n is negative. So what happened here? Suppose n is like minus 2. So what is x to the power minus 2? We are defining it to be x inverse raised to the power 2, for which you refer to or consult with that part of the definition. You can raise any group element to positive indices by that, and here mod n is necessarily positive, right? If n is negative, that mod n is positive. So this is meaningful. This is just you multiply x inverse with itself mod n times. So this is a natural definition. This is really an extension of the definition of exponentiation that we are used to when we deal with real numbers or complex numbers. We are just extending that definition to any arbitrary group. One thing that we should note here is that if G is abelian, then instead of writing x to the n, many times we just write nx. So then x to the n is usually denoted by nx, or more precisely or more clearly n dot x. So this dot is not any binary operation on the group because there is no meaning. I mean, you can't, the integer n is not an element of the group, so you can't call it the binary operation on the group anyway. It is just a notation to further emphasize that you're adding x with itself n times. When the group is abelian, the binary operation is usually thought of as an addition rather than a multiplication. So this is just fostering that thought. Okay, so I hope this notation is clear. And I don't know what I have here. I have some example to illustrate the notation. So what about, and this is an abelian group, so I don't want to use the exponential notation. I'll use the scaling notation. This is kind of scaling notation. So let's see. What about 7.2? And maybe it's better to put bars here because otherwise it could get confusing. So this time I'm going to put bars on top of them to emphasize that these are remainder classes modulo 5 and not just ordinary integers. So we can talk about 7 times 2 bar. 7 times 2 bar is, by definition, you're adding 2 bar with itself 7 times. So it is 2 bar plus 2 bar plus dot dot dot. But the way the addition behaves on Z mod 5Z shows that this is nothing but 7 kind of goes inside, and now the inside is an ordinary multiplication, which I will write as ordinary multiplication is written. So it's this. It's the remainder class of 7 times 2, which is remainder class of 14, but we are working modulo 5, so this is remainder class of 4. So I hope this notation is clear, and you can further experiment on other groups that we learnt about as to what this notation is trying to do. What is important is we realize that some very simple exponentiation rules which we are familiar with from high school hold even in the context of an abstract group. If G is any group and X is any group element, then for any integers m and n, not just positive integers, but for any integers m and n, this holds. just like in real numbers. This also holds, but here there is a little catch. We can't write xy inverse as x inverse y inverse. That we can't do. The inverse will pull the y part on the left side, so it will reverse the order in which things appear, just like transpose. In linear algebra, when you take transpose of the composite of two endomorphisms, the order in which the endomorphisms appear switches. Or not necessarily endomorphisms, the linear maps, the order switches. Similarly, for inverse operation, the order switches. And the last thing we are saying is that first you exponentiate by n and then you exponentiate by -1, you get x to the power minus n. In fact, we can generalize this in the fourth point, that x to the power m, or let me write it this way, x to the power n to the power k equals x to the power n times k for all integers n and k. All the rules that we are already familiar with from algebra on real and complex numbers. They are exactly those rules. Except here one has to be a little more careful. Okay, so this fourth one generalizes the third one, because when you substitute k as -1, you get the third one. That's great. So let us see why these are true. I don't want to write down formal proofs of these, but let us at least see why these are true. Proof of the first thing, what about, let's say m and n were positive. What about this? Clearly this is going to be x to the power 2 times x to the power 3, because by definition this is x times x 5 times. We are just grouping these two together and calling it x square, and grouping these two together calling them x cube. So if m and n are positive, then this is very clear. What if they are both negative? Well, suppose they are both negative for the moment. Suppose we had something like this. Then it is nothing but this thing. But now by definition of this notation, it is equal to x inverse raised to the power 5. That's how it is defined. Just look at this part. And now what is this? This is x inverse 5 times. So we will group the first two together and the rest two together. But this we already, we just saw this. This can be written like this. And now again use the definition of the exponentiation. This is x to the power -2, the first thing, and the second thing is x to the power -3. So it checks out. And now let us just look at one more instance of this. You have x to the power 2 -3, let's say. So how would you deal with that? So this is, you can write this as x to the power or x inverse to the power. Yeah, how do I explain this? Maybe I'll choose some other numbers. These are not the best numbers to choose. Let me explain by 4 minus 7. Okay. So by definition, or by just ordinary subtraction, this is equal to this, which is x to the power or x inverse to the power 3, which I will write as x inverse to the power 7 minus 4. So instead of 4 minus 7, I'll write it as 7 minus 4 here, adjusting for it by writing an inverse here, and all these steps should be clear to you. This is where I used this definition. Everything else is just logical. So this is equal to x inverse. What do I want to do? I want to show that this is x to the power -3, right? So so this is equal to x to the power -1 to the power 3, because 7 minus 4 is 3. And now this is equal to, by definition, x to the power -3. Just by using this definition, I get this equality. So you can justify this for any pair of integers m and n, both positive, both negative, one positive, one negative. You can just play around. You can write the general proofs. I have explained these via examples. You can write down the general proof. And let me leave everything else as an exercise. Maybe I'll do the second one, but everything else as an exercise. So this will be exercise, that will be exercise. The second one We want to show that xy inverse is y inverse x inverse, but just note that y inverse x inverse, if you multiply that with xy, what do you get? This, once we bracket it in a different way, which we can by associativity, we get this is equal to y inverse identity y, which is y inverse y, which is identity. So we see that this times that is identity, and hence this thing is the inverse of that thing, and that is what is written over here. Alright, so very simple. Let's proceed. So this leads to what is called the cancellation property, or maybe not this leads to, but whatever. Fix a group G. Suppose we have three elements A, X, Y in G, and suppose it happens that AX is equal to AY. So then we are saying that necessarily X equals Y, and the converse is anyway obvious. If X equals Y, then clearly this holds, but the converse is really the main content of it. If AX is equal to AY, then you can kind of cancel A off. That's why it's called the cancellation property. You can sort of cancel A off to get X equals Y. Right? And similarly for the multiplication on the right side. The reason is very simple. Proof: if we have AX equals AY, multiply by A inverse on both sides, and it will give you X equals Y. So we are not using the previous proposition or anything, just the basic properties of inverses. Similarly, you can do the second part. So this is the cancellation property. And a nice consequence of the cancellation property, or a repackaging of it, is the following. Fix any group G. For each element G in the group, define this map mu G as follows. Define mu G as mu G of X is Gx for all X. So it is kind of the multiplication by left. Mu, I have chosen the symbol mu to emphasize the multiplication. Mu, M for multiplication. Okay, so I hope this map is clear. And we claim that mu G is a bijection. We are not even assuming that the group is finite, any group. So why is mu G a bijection? Proof. Well, one way to prove it is, note that mu G inverse composed with mu G is mu E. Maybe first I will write down a proof in a more basic language. So injectivity of mu G, fix a G, and let's justify injectivity. For injectivity, say mu Gx equals mu Gy, then Gx equals Gy, and now by the cancellation property we get X equals Y, and that justifies injectivity. Because what do you need to do to show injectivity? You want to show mu G is injective, so if it takes the same, or it produces the same output on two inputs, those two inputs must be the same. That is exactly the definition of injectivity. For surjectivity, let Y be in G, then we just need to show that it is in the image of mu G. But mu G of G inverse Y, maybe I should have called it X, but anyway, mu G of G inverse Y is G inverse Y, which is EY, which is Y. So surjectivity is also fine. So mu G is a bijective function. Maybe it is better to observe that mu G composed with mu H is mu GH, and mu E is just the identity function on G. So take this as an exercise, these two statements as exercises, and using that also you can deduce this proposition. But anyway, it's better to see it using an instance of cancellation property, because that is what I was going to, or trying to illustrate. So mu G is a bijection, and now this has a very nice consequence. So the nice consequence is, just like in the proof of Fermat's little theorem, we have a certain argument. We can reproduce that argument in this abstract context of an abelian group. fix a finite abelian group, we are going to reproduce the most common argument used to prove Fermat's little theorem. So what are we going to do? Yeah, but what is the statement? The statement is that fix any element in G, then x to the power G. Even though it is an abelian group, I'm using the power notation. That is not a problem. It's not mandatory that for an abelian group you use the additive notation. You can use the multiplicative notation. I'm using the multiplicative notation. So we want to show that this is true. Why is this true? Very interesting argument, but it is same as the one used for Fermat's little theorem. So what we have is, maybe I'll write, it's okay. So fine. So we have this bijection mu x, right? This is a bijection, and therefore this product is equal to this product. Now what happened here? What is this notation? This notation is you product all the elements of G. Now for that to even be well defined, this notation to be well defined, G has to be abelian. Because in an arbitrary group, it matters in which order you multiply things, right? Associativity only says that you can bracket whichever way you want. It doesn't allow you to shuffle the things around. That is allowed by abelianness or commutativity. So that is why this notation makes sense. You take any group, you're allowed to multiply all of them. In any order you want, you'll get the same answer if the group is abelian. So this notation therefore makes sense. If you want to multiply things in an arbitrary group, or say multiply all the things together in an arbitrary group, you can only do after introducing an ordering. So it will be order dependent. Anyway, so now I hope you understand that this product is same as that product because of the bijectivity of mu x. The elements that appear in this product are exactly the same elements that appear in this product, namely all the elements of the group G. So that's fine. But what is the left side? The left side is what it is. The right side is x times G, which is equal to x to the power mod G times what is there on the left side. So this we need to understand. So what is going on? On the right side, we have xg times xh times xk, where h, k, g, these are all the elements of the group. So x will appear mod g times. And since, again, the group is abelian, so we can collect all the x's on one side and everything else on the other side. So we have this. But now this is equal to that. And now by the cancellation property, because the left side we can think of as identity times something. So by the cancellation property now, this gives us that E is equal to x to the power mod G. And this is exactly the proof of Fermat's little theorem that is usually given in a course on elementary number theory, like in my course. So it's very nice, like a general result about abelian groups. And later we will see that to prove this, you don't need the abelian hypothesis. That's very interesting. Right now we are not in that position to prove it, but you don't need this. Don't need. We'll prove that later. So that's very interesting. That's already a generalization of Fermat's little theorem, if you will, or Euler's theorem. Okay. Yeah. I think that's it for today's lecture. As usual, like, comment, share, subscribe, and I will see you next time.